Okay, let's try to finish up section 9.2 now. So we're talking about the uh, t-distribution, and we're looking at building a confidence interval about the population mean. We're on problem 8. It says that a Gallup poll conducted in 2013 here asked 1,039 randomly selected Americans age 18 and older, roughly how much money do you think you'll spend on Christmas gifts this year? Results from the survey indicated that the sample mean is $704 and the sample standard deviation is $65.72. When I first saw this, the sample mean there, I was pretty blown away by that. That's the average that Americans 18 and older spent during that year. I don't know, I guess I'm just cheap. That sounds like a lot of money. But anyway, all right, so that's the information. Part A, we want to verify the requirements for constructing a confidence interval about the population mean. Okay, so we want to find or have an idea of the actual average of all Americans age 18 and older, the dollar amount that they would be spending on Christmas gifts during this year. Okay, now of course there's no way to know that, but that's what we're trying to build an interval of numbers where we think the population mean is located. So before we can do that, we need to verify that we can construct this interval. Condition 1 says that the sample has to be at least 30 or more for non-normal populations. Now, they didn't tell us if the population was normal or not. My guess is that it would not be normally distributed. Dollar amount spent on Christmas gifts, I think, are going to vary all over the board, and I don't know that that would produce a bell curve. It probably wouldn't. Okay, so condition 1 is satisfied, though, regardless, and also the sample is less than 5% of the population. Okay, the population would be all Americans age 18 and older. There are millions and millions in that population. 1,039 is quite a bit less than 5% of millions and millions. Okay, so the two conditions are satisfied, and we're able to build the interval now. We're going to use our calculator to construct a 95% confidence interval for the average amount of money that Americans age 18 and older spent on Christmas gifts in 2013, and then we'll give an interpretation of that. All right, so if you have the 83 and 84 model, here's how this would go. I'm going to hit stat and then go over to tests, and I'm going to want t interval there, and then it's going to ask, do we want data or stats? We have statistics given to us, and so I'm going to highlight statistics and enter in the stats that were given. The sample mean was 704. The standard deviation was $65.72. The sample size was 1,039. The confidence level is a 95% level for this one. Make sure that's in decimal form. Hit calculate, and there's our interval. Okay. So the interpretation of this would be to say that we are 95% confident that the average amount of money that Americans age 18 and older spent on Christmas gifts in the year 2013 is somewhere between $700 and $708. Okay. If you have the Inspire model, here's how you do the calculation. So if we just hit enter here, and then hit menu, and then go down to statistics, and we're going to want confidence intervals, and then we want t interval. Okay, and we have the statistics given to us, so I'll make it say statistics, hit OK. You're going to enter in pretty much the same information here. It's going to be the sample mean is $704. The standard deviation was $65.72. The sample size was 1,039, and we're working with a 95% level in this, I think. Yeah, and so hit OK. And okay, so the lower bound is 700. The upper bound is 708, which is what we're getting there also. Okay. Part C, could the previous interval be used to estimate the average amount of money Americans under 18 years of age spent on Christmas gifts in 2013? No, obviously it couldn't, because it's a different population, right? So we have no information for how much money Americans under 18 would spend. I mean, my guess is going to be obviously quite a bit less than $704 if you're going to be looking at children and young adults. Okay, so let's take a look at problem 9. A Gallup poll conducted in 1950 asked 1,031 Americans, how often do you bathe each week? It was found from this group that were surveyed that they bathed an average of 3.7 times a week, with a standard deviation of 2.3 times a week. So we want to build a confidence interval about the population mean. We're going to verify that we can do that first in part A. Verify that the requirements for constructing the interval are satisfied. So the sample size is bigger than 30. Now again, they're not telling us if we have a normal distribution or not. My guess is that for this it would be, though. Okay, if you look at the number of times that Americans bathe in a given week, I think it'd probably be an average of about 3.7, as they said, and you'd be looking at something that would be roughly bell-shaped and symmetric. They didn't tell us that, though, but so we're still all good with the first condition there. Also, the sample size is less than 5% of the population size, because there's still millions of Americans even back in 1950. 1,031 is quite a bit less than 5% of millions. Okay, part B. We're going to use the calculator to construct a 99% confidence interval for the mean number of times that Americans bathe each week in 1950. So I'll use the 84 model here again. If we go stat over to tests and then down to t interval, again we have stats given to us here. X bar is 3.7. The standard deviation is 2.3. The sample size is 1,031. We're building a 99% confidence interval. Okay, calculate. And I'm getting 3.52, 3.88 if you go nearest 2 digits on that. So this interval would be my answer. And the interpretation then, we're 99% confident that the mean number of times that Americans bathed each week in 1950 is somewhere between 3.52 times and 3.88 times. Now in part C, it says, suppose that the sample size for this study was 1,500 Americans, and assume that the point estimators happen to remain the same, just for the sake of calculations here. Use the calculator to construct a 99% confidence interval for the mean number of times Americans bathed each week in 1950, and then we'll compare that to what we did in part B. All right, so let me go through this again here. I'll hit stat, go over to tests. I want t interval. The only thing that's changed from what it was before is n is 1,500 this time. And if I hit calculate, I'm getting a new interval here. 3.55 and then 3.85 would be my upper bound. So, okay. We're going to compare this interval to what we got in part B. How does increasing the sample size affect the margin of error? Well, we'd want to observe that this interval is smaller than the one that we had in part B. In general, the margin of error is going to decrease. That's what gets you the width of the interval, which is, again, the smaller here. The width is going to decrease as n increases. Okay, and I think that should make sense to us. I mean, if the sample size increases, that's a good thing, right? Because we have more information in front of us, and so there's less of a chance at making a mistake. The margin of error is going to go down if you have more information in front of you. In general, that's going to happen. Okay, let's take a look at problem 10. Next, this is the last problem here. It says that an arborist is interested in determining the mean diameter of mature white oak trees, and the following data represent the diameter in centimeters, 1 meter above the base for a random sample of 18 mature white oak trees in the forest preserve. Treat the sample as a simple random sample of all the white oak trees in the forest preserve and assume that the population is normally distributed. Okay, so here's our data set, and in part A, we are going to use the data to compute a point estimate for the population mean diameter of a mature white oak tree 1 meter from the base in the forest preserve. Of course, you could add up all 18 numbers and divide by the total to get the mean here. It's roughly 49.3 centimeters would be the average diameter here. Another way that you could get this is you could use the lists. I'm going to be using the list here in just a moment for the next calculation, but I've already got the data entered into L1, and so if I hit stat, go over to calc, one var stats, I've only got one variable here, hit enter. Okay, there's the mean is roughly 49.3 then if you go nearest one digit. Okay. Now, part B, use your calculator to construct a 98% confidence interval for the mean diameter of a mature white oak tree 1 meter from the base in the forest preserve, and then we'll interpret that. Okay, so this time I actually have the data. So I'm going to go to stat and go over to tests and then go to t-interval just as before. Only I'm going to highlight data now, and I've already got the data entered into L1. Okay, if it didn't say L1 there, I'd hit second 1 for L1 to show up. Frequency of 1, I want to use each number one time, and the confidence level here is a 98% level, so I'm going to change that, 0.98, and hit calculate. And it gives me my interval then, which is 43.74 is the lower bound, 54.93 is the upper bound. Okay, I was going to show you real quick how to do that on the Inspire model. So if you go to lists and spreadsheets, and I've already typed in the data just to make this go quicker into this column here, and I'm going to hit menu, and then go to statistics, and then go to confidence intervals, and then I want a t-interval. I'll hit enter. It will ask me, do I want data or stats? Okay, this time I've got the data entered, so I'll keep data there and hit OK. The list is A. That's where the data was entered. I'm using a frequency of 1. That looks good. And the confidence level is a 98% level here. We'll give the results in column B. And hit OK. And yeah, so you see that these are the same numbers I'm getting there for the lower bound is 43.74, the upper bound is 54.93 if you go nearest two digits. Okay, the interpretation would be to say that we are 98% confident that the mean diameter of a mature white oak tree 1 meter from the base in the forest preserve is between 43.74 centimeters and 54.93 centimeters. Of course, be specific. We're looking at the average diameter, not the average radius or some other measurement, okay, of a mature white oak tree. Indicate, the kind of tree that we're looking for. We're 1 meter above the base, so the measurement is not anywhere, it's specifically 1 meter from the ground. In the forest preserve, okay, we're not, in other parts of the world, okay. So again, be specific. And of course, if this were a large forest, like it'd probably be very difficult to get the average of all the mature white oak trees 1 meter from the base, to take measurements. That could be a very time-consuming, brutal thing. So, but we're 98% sure that if we went through that procedure, we can have an idea of where the mean is located here, based on the information from this sample. Part C, could we have computed the previous confidence interval in the problem if the population had not been normally distributed? So they told us that the data is, we're assuming that the population is normally distributed. Now that probably could be very easily overlooked, but it's actually a key part of this problem, because if they didn't tell me that, then no, my calculation here would not be meaningful, because I don't have a sample that is at least 30, okay? You have to have a sample that is at least 30 for non-normal populations, otherwise the interval is a waste of time. It's, it didn't fit the initial condition, yeah, so it's, of course you want to make sure that the conditions are satisfied. All right. That's all I had then for the chapter and also for the course. So here's your last homework assignments, page 401 and 9.1, and then page 412 and 9.2.